So thank you very much for the invitation. And actually today I will go to the Kummer varieties only around the end of the talk. Before I will speak about some relationship between the monodromy group of hyperkähler manifolds and the Rampol cone. So since I'm the first one to speak about them, let me give some definition. So let X be a compact and Kähler manifold then we say that X is hyperkähler if it is simply connected and its H20 is generated by a single form which is symplectic. So we already saw some examples like K3 surfaces. And some more examples are built from the two symplectic surfaces we know. So the symplectic Abelian surfaces or K3 surfaces. First one is the Hilbert scheme of zero-dimensional subsets of the K3 surface. So we take Hilbert of S, where S is a K3. And we usually denote it also as S square bracket of n. This manifold is hyperkähler, and so it is simply connected, and it inherits a 2-0 form from the K3 surface. And also we have a map from this Hilbert scheme to the symmetric product, which is usually denoted the Hilbert-Chow morphism. Which sends an length n zero-dimensional scheme to its support. And all deformations, well, all smooth and Kähler deformations of Sn are hyperkähler, and they are called manifolds of K3n type. A similar example are the generalized Kummer manifolds, which are roughly the same construction but with an Abelian surface. So we let A be an abelian surface, and we take the Hilbert scheme of n plus 1 points with its Hilbert-Chow morphism. So this is not simply connected, but we just make it simply connected. So we take the summation map, mapping n plus 1 points to their sum on A, and we set the nth generalized Kummer variety of A as the inverse image of 0 in this composition. And this is called generalized Kummer manifold. And the name comes from the example with n equals 1, because K1 of A is the Kummer surface, well, the Kummer K3 surface. Okay. So already in the examples, there seems much in common with the K3 surfaces. And indeed, the main tool I will be using is the so-called Bovil-Bogomolov-Fujiki form. So let X be hyperkähler. Then there exists Q, a quadratic form on H2 of X with integer coefficients and a constant C such that for all classes in the H2 the top intersection form of this class is the constant times the quadratic form to the n, where the dimension of X is 2n. And this is the Bovil-Bogomolov-Fujiki form. So this allows us to define some cones inside the real H2. So the positive cone Cx inside the 1,1 real part of X is the connected component of the cone of positive classes which contains a Kähler class. So it is easy to see that all Kähler classes lie inside the positive cone. And the Kähler cone K of x is just the cone of Kähler classes. And finally, the birational Kähler cone bk of x is the union of the pullback of Kähler cones taken along all birational maps from x to another manifold x prime, where x prime is hyperkähler. So this is well defined because the canonical divisor is 0, so in the indeterminacy locus of these maps will be of codimension at least 2. So on divisors, everything is fine. So the subject of the talk is the monodromy group. So let me define what I mean. First of all, a parallel transport operator is an isometry from the H2 of x to the H2 of y with x and y hyperkähler obtained, well, by parallel transport along a smooth family. And the group mon2 of x is just the group of parallel transport operators from x to itself. So in principle, one should consider the action of a parallel transport operator on all the cohomology. But for the purpose I'm interested in, only the action on the second cohomology is relevant. And an example, well, mon2 of a K3 is simply all orientation preserving isometry. And okay. So one more thing is that the Boville-Bogomolov form allows us to identify the H lower 2 as the dual lattice of the H upper 2. So this form gives an embedding of H2 x z into H upper 2 x q. And from now on, I will always see curves inside this second cohomology. So the last definition for now, we take D a divisor then we call it a wall divisor if, first of all, its square, well, its square is negative with the Boville-Bogomolov form. And second of all, for all monodromy operators, which are also Hodge isometries, we have that the orthogonal to D does not intersect the birational Kähler cone. Or equivalently, we could do the same with the Kähler cone. And I will explain in a minute why. So this definition seems quite artificial, and indeed it is artificial, but this is the definition which behaves better from, with respect to deformations. Of course, this class of divisors is invariant by monodromy operators, which are also Hodge isometries, just by definition. And no. Let me use a okay. So one first example of wall divisors can be given in the case of K3 surfaces. And if X is a K3, then D is a wall divisor if and only if D square is minus 2. So in the case of K3 surfaces, these divisors actually cut out the positive cone in several chambers, and one of them is the Keller cone, or the Neff cone, well, the ample cone if you prefer to work only algebraically. And the same holds also in higher dimension, actually. And this is by the following proposition. So X is, as usual, hyperkähler, and D is a wall divisor if and only if there exists a G which is a monodromy operator and a Hodge isometry such that f of D is a multiple of an extreme array of a generator of the Morricone. Here I don't have necessarily the Morricone of X. I might have the Morricone of a different manifold birational to X. Manifold X prime birational. So here, with multiple of such a generator of an extreme array, I mean with this embedding. Oh, no, I shouldn't have changed it with G, probably. Okay, so how to prove this? Well, without loss of generality, let me prove it in the case X is also projective. This is because there's a very nice description of this group in the projective case. In the non-projective case, the group is not the one I'm going to tell you, but still everything works fine. So this is a theorem of Markman, which says that if we have a projective hyperkähler manifold, then the group, well, let me denote it with Hodge down here to mean that they are also Hodge isometries. This is a semi-direct product of two groups. So these are also birational self-maps. And this W is indeed a Weyl group of reflections. And W is generated by reflections on reduced and irreducible divisors of negative square. So part of the theorem is also that these reflections are integer isometries, which is non-trivial in principle. In the K3 case, these reflections are reflections on -2 vectors, so everything is fine. And these are only the automorphisms of the surface. Mm-hmm. Which have the same action of a birational self-map. Yes. I mean, I take parallel transport operators induced by a birational map, because the parallel transport, I can take the two small deformations which link the two birational manifold, those given by Huybrechts. Well, in practice, I'm taking the induced isometries induced from a birational transformations, and I'm saying that these are of parallel transport. Yeah, this is the easiest way.
So this expansion is just something birational to
No, hyperkähler too. Yes, yes. Well, no, I consider it as a self map. Yeah, X prime is hyperkähler. Yeah, I don't go outside of the hyperkähler setting. So with this, let me prove this statement. Let me start with this direction. Well, since we have this action of birational self-maps, we can actually suppose that we start with an extreme array on X itself. So let R be a generator and let D equals a multiple of R be a primitive divisor. So the primitive is not needed because the definition of whole divisor doesn't ask it, but just for simplicity. So the claim is equivalent to proving that a multiple of G of R is an effective curve. So as R is a generator of an extreme array of the Morricone, R orthogonal, which is the same as D orthogonal, does not intersect the Kähler cone of X. And if this curve stays effective for all monodromy Hodge isometries, then also the orthogonal to this curve will not intersect the Kähler cone. So we can suppose the transformation G is as simple as possible. So we can take it either here or inside here. And we try to prove that this curve is still effective. So let E be a reduced irreducible divisor with Q of E negative, and let R of E be the reflection which lies inside W. So R of E of D is going to be D plus the integral over a curve of D times E, where C is the dual effective curve. Which is fully contained inside E. And in the same way, by duality, we get what is the reflection along E of the curve R, which probably now is a bad choice of a letter. So as R is an effective curve, its image is still an effective curve, because this integral will be positive. So RE of R is still effective. And this settles all elements of W. So now we take G, an element in Mon2 birational of X, and so this is some self-map from X to X, and here we resolve the map. So if R does not lie in the indeterminacy locus of G, then of course G of R is effective. And if R is in the indeterminacy of G, well, then R is an extreme array of the Morricone, so we can also contract R. And we can also take the map G to be as simple as possible, so that the indeterminacy locus contains only a single curve class, and then we can build all the other maps from elements of this kind. So we also have a contraction here. And so G of D is well defined. And P2 R is a curve in the fibers of P2, and also we have R prime, which is a curve in the fibers of P1. So now here we contracted only the class R, and this gives us also that Y as a smaller second Betti number by 1, and what goes to 0 is precisely D, because it is a multiple of R. So here we are contracting R prime, and what happens is that also R prime must be a multiple of G of D. We don't know if it is positive or negative. So G of D is some multiple of R prime. And we extend the map G to the rational H upper 2. So we have it also well defined on R. And this means that G of R is, well, yeah, we don't know the sign, be R prime. It's be also negative. So a multiple of the image of R is still effective. So one direction of the proposition is done. The other direction is actually the easy direction. So the fact is that the action of this Weil group divides the positive cone into chambers one of them is given by the birational Kähler cone, closed, and we take the interior of this. And W is transitive on these chambers. So this sentence is actually the easy part because it's part of the theorem of Markman. So these reduced and irreducible divisors of negative square which generate this group are a slightly weaker version of wall divisors. They don't distinguish the different birational models, but they allow us to know the birational Kähler cone, or at least its closure. So since d square is negative, we have that the orthogonal intersected the positive cone is non-empty. And now we take this D, and since the action of this Weil group is transitive on this chamber, we can move it around with the Weil group in such a way that this orthogonal will intersect this chamber. Well, the closure of this chamber. So there is G in the Weil group such that G of D perp intersected the closure of the birational Kähler cone is non-empty. But this intersection is empty with the interior of this, well, with the cone itself. So simply, for dimensional reasons, this hyperplane will support a face of the boundary of this cone. And a face of this boundary is dual to an extreme array in some birational model. So actually, G of D perp, G of D is a multiple of an extreme array in some birational model. So this strange definition of divisors is actually taking multiples of extreme arrays and moving them around with monodromy. And the point of doing this is the following theorem. So let X and Y be hyperkähler manifold with X the formation equivalent to Y. Let D be a whole divisor on X. Let F from the H2 of X to the H2 of Y be a parallel transport. Operator. And we finally ask that the image of D is still algebraic. So with all these conditions, we have that f of D is a whole divisor on Y. So here the examples of K3 surfaces is slightly misleading, because on K3 surfaces all whole divisors are effective, while in the general case, a whole divisor need not be effective. So today I will not prove this result, but its proof is very, very close to the proof of the Torelli theorem. It's a sort of proof by contradiction on this.
Close, what do you mean? You use the same method or
Basically, yes. No. It's close because I take a moduli space of manifolds where this class is algebraic. I have a nice period domain associated to it. I've got a period map. And I suppose that there is some point somewhere where this element is not a whole divisor. And from that point, I can construct enough twistor lines to cover all the period domain. And I get a contradiction on the initial assumption that this divisor was a whole divisor on X. Okay. So what's the point in this is that whole divisors are actually computable in most of the known examples of hyperkähler manifolds. And this is done in a completely different way, which relies on stability conditions on the derived category of K3 or Abelian surfaces. So as an example, we take the easiest four-dimensional case. So let X be a K32 type manifold. Then D is a whole divisor on X if and only if D square is -2 or D square is -10 and the divisibility of D is 2. So in this case, well, actually, up to isometry, there are two kinds of element of square -2 in this setting because H2 of xz is the K3 lattice plus an additional class of square -2. So an element of square -2 can have divisibility 1 if it comes from here, or divisibility 2 if it comes from this part. And in the case of square -2, there is always a multiple of this divisor which is effective. In this case, no multiple is effective, and is actually a result of Hassett and Schinkel that this element is dual, well, at least generically, is dual to a class of a curve lying inside a P2. I should say that here there is a similar result, well, almost equivalent, by Bayer, Hassett, and Schinkel. So the way I will compute the monodromy group for generalized Kummer manifolds is through a simple remark following this theorem, which is the following. Yes, there is a nice way to write it, which I don't remember by heart, but it relies on the embedding into the Mukai lattice. And the nicest way to describe it is by describing the rank 2 lattices generated by the wall divisor and the Mukai vector. But it can be written down completely. So the fact is that we have an inclusion of groups where mon2 Hodge of X sits inside a bigger group G, where G is the group preserving wall divisors. So if we know what are wall divisors in a given manifold, as a set, yes, wall divisors as a set. So if we know how to find wall divisors, we can compute this group G, and this will give us a upper bound on this mon2 Hodge. So this upper bound itself is not enough to compute mon2 Hodge, but in some cases, well, actually in the generalized Kummer cases, there was already a lower bound. And the nice thing is that these two bounds coincide. Yes. So here I'm taking elements which are also Hodge isometries. But if I take a random element in mon2, then I can deform the manifold in such a way that it becomes Hodge isometry. So I'm really not making any restriction. What I will compute is mon2 without the Hodge. So second part, generalized Kummer. Yes?
On the theorem over there, in the box there is a parallel transport such that, is it satisfied whenever D remains algebraic? Or is it stronger?
No, that's not for granted, I think. No. You must impose that the isometry is of parallel transport. Okay, so first thing is that the H2 of Kn of A over Z is very close to the H2 of an abelian surface. So we have 3 copies of U plus an additional class of square minus 2n minus 2, which I will call delta. And 2 delta is the exceptional divisor of the Hilbert-Chow map restricted to our Kummer manifold. And also, there is a canonical, well, here I'm speaking really about only this manifold, not all generalized Kummer manifolds. So this canonical embedding should still exist, which sends the H2 of Kn of A inside the even cohomology of the Abelian surface, integer, and H2 Kn orthogonal is generated by V, which is 0 in the H2 part of A, 1 in the H0, and n plus 1 in the H4. So there is this canonical choice of an embedding, which is actually equivalent to building this Kummer manifold as a particular moduli space of sheaves on this Abelian surface, where the sheaves have this discrete invariance. Yes?
No, just to put on delta, what is going delta?
That's important. So delta, let me give a name, F. F is no longer anywhere, so now F is, so F of delta is 1, 0, and minus n minus 1. This is actually very important, and I will be using it soon. So since I want to use the description of wall divisors, there better be some such description, and indeed, it's a result of Yoshioka. So which, well, it's phrased in different terms, but it says that D is a wall divisor on Kn of A if and only if the saturation of the lattice generated by V and f of D, which I will call T, contains W such that W square is positive and W square is strictly smaller than the pairing between W and V, and smaller than V square divided by 2, which is just n plus 1. So, as an example, and T is indefinite. which is surely needed as a wall divisor as a negative square and v as positive square. So as an example, if we take t equals to 2n plus 2, 1, 1, 0, where this is w, this corresponds to a wall divisor inside the H2 of Kn, and this d as square minus 2n minus 2 and divisibility 2n plus 2. So it is numerically equivalent to this delta. And what I will use is that these wall divisors form a single isometry orbit. Which means that if I take, well, later on I will take the image by a monodromy operator of this element, and the lattice they will generate when I take this saturation after the embedding will still be this lattice. Yes, yes, it's Eichler, as usual. So now I need the lower bound for the group. So let me consider two maps from the orientation-preserving isometries. The first one is a map which takes an isometry and gives me its induced action on the discriminant group of the H2, which I will call chi. And the second just takes the determinant of an isometry. So this discriminant group is cyclic, and for every value of n, we always have the plus and the minus isometries. For bad values of n, there can be more isometries. So we take n as the pre-image by chi of the plus and minus isometry. And W will be chi times the determinant restricted to n, the pre-image of 1. So here we are just taking elements of this n, where if they act as -1 on the discriminant group, they have negative determinant, and vice versa. So the lower bound is again a result by Markman, which says that n intersected with mon2 of x is W. So already this is an almost full computation because the index of this n inside the full isometry group is finite and usually very small. So now the final result, as you will see, is just a quick computation and says that mon2 of x is actually W. So to prove it, we prove that mon2 of x, well, of course, it will sit. OK, this mon2 of x is actually a subset of n. And then we just apply Markman proposition. So let us take an element in mon2. And we take delta as before. So g of delta will be some multiple of delta plus a non-primitive element L, where L is in delta perp. This is just because the divisibility has to stay the same. So key of G is going to be the class of this K over here. And we want to prove that K is congruent to plus or minus 1 modulo 2n plus 2. Also, we have that V, the saturation of V, and I called it F, right? Yes. F of G of delta is the same lattice. So this means that V plus G of delta divided by 2n plus 2, F of G of delta, sorry, is in H2 star of A, or the same thing with the reverse sign, V minus F of G of delta. So that they can generate this lattice. And let S be V minus F of D divided 2n plus 2, which by this description, it lies in H2 star of A. And let me give names to this. T for the first one and T prime for the second one. So either T minus L minus S or T prime minus L minus S lies in H2 star of A. And here comes the contradiction, because this is K plus, yes, plus 1 times delta divided by 2n plus 2, and this is K minus 1 delta divided 2n plus 2. Perhaps I got the signs wrong. That's quite likely. T minus S plus, no. But now delta is a primitive element in this cohomology. So either K plus 1 or K minus 1 must be divisible by 2n plus 2. So this implies that K is congruent to plus or minus 1 modulo 2n plus 2, which means that mon2 is actually contained inside n. And therefore, we're done. And a similar reasoning can be applied also to the O'Grady sporadic 10-dimensional example to prove that the monodromy group is not the full isometry group of the lattice, which was conjectured. But in this case, it's quite hard to get a good lower bound for this group. So the result is just a counterexample and not a theorem. Okay, thank you very much.